Hey everyone, my name is Venerin, and in the next couple of videos, I'm going to show you how you can use LayoutLM version 3 for document classification. First, we're going to have a very brief look on how LayoutLM version 3 differs compared to the previous versions, and then we are going to continue with the HuggingFace implementation in the Transformers library of that same model. We're going to have a look at our dataset, which is basically a couple of HTML documents that we need to convert to images so we can use with LayoutLM version 3. And I'm going to show you how you can use the preprocessor, which includes a feature extractor and a tokenizer. And then we're going to pass in the inputs to the model itself. In the next couple of videos, we are going to make a more deep dive into what LayoutLM version 3 is. And then we are going to use PyTorch whitening to fine-tune the model on our dataset and evaluate it. So let's get started. So what is LayoutLM version 3 and why it is important? Well, there is this paper on arXiv that is published in April during this year. And LayoutLM version 3, pre-training for document AI with unified text and image masking. That's the name of the paper. And it's, of course, open sourced on arXiv, and you can open it right here. And the first thing that you will notice here is that those types of models work or are like built to work on documents. And you can see, for example, right here, there is understanding of some texts. And here you can see that it is also those type of models are interested into the layout of the documents themselves. Let's see if we have another example of images, but no, not really in here. So what this does is to work on a variety of tasks or techniques called document AI. And in here, LayoutLM models or the family of those models, as well as other models like Bros or whatever, are basically using transformers for the text preprocessing. So they have tokenizers, very similar to BERT and other transformer models, but also they embed the layout of the document, and they do that at least in the first version of LayoutLM. They did that only using the bounding boxes of the texts, but now in LayoutLM version 2 and 3, they actually use the image, an embedding of the image itself. So the model is basically given the input of the text, then the bounding boxes. As you can see here, we have different colors for the bounding boxes, but also the whole image of this document or this page. So this is a very interesting combination of three different inputs, and the results on those type of models are actually state of the art, and they work very well. So in fact, they worked very well, so well that Microsoft Research published an open source version of the models, and they have the weights and everything. And you can also use this into HuggingFace Transformers library. So this is what we are basically going to do. And what is so special about LayoutLM version 3 compared to the second one, it is using a transformer, or not a transformer, but it is using a similar technique as the vision transformer, which is called patch embeddings. And there is a very good tweet from Niels Roge. I'm sorry if I'm butchering his name, but he basically explains that the backbone that was basically the image embedding of the LayoutLM version 2 is now replaced with these patch embeddings, which are very similar to the vision transformer. And it appears that this is kind of work even better. And you can see an example here from the image patches. So again, if you're somewhat familiar with the image transformer, you can guess that this document is actually split into smaller squares, which are then passed to the transformer. And again, we have pretty much the same thing that we have for the words or the tokens. And then we also have an embedding of the bounding boxes of the words. So yeah, you can pretty much go into deep or a bit more details of how this is done. They have a very good paper and they explain a lot more about the tasks and the difference between this model and the previous models. But I'm going to dive a bit deeper into those in the next couple of videos. Here we are just going to get our feet wet and basically have a feel about what is happening. So the task that we are going to work on is document classification. And in this couple of videos, we are going to get this Kaggle dataset, which is provided by Dr. Anonymous, and it's called Financial Documents Clustering. So these are basically 5 different classes of documents that are available from financial annual reports done by Hexaware Technologies. So their financial annual reports. And those are basically the 5 different categories. And you can see that this is very imbalanced data set, but still we're going to work with that. We have around 2,500 examples. And the interesting thing about this dataset is that it is comprised of HTML documents, but not images. So we are going to do some hacking around that and convert the HTML documents into images. And so let's start with a brand new Google Colab notebook. And in here, I'm going to copy and paste a lot of requirements that we need for this. And I'm going to install those. And then I'm going to pretty much do the same thing for the Ubuntu requirements, or the machine that we're going to use. So here I'm installing the Selenium library, which is an automation or browser automation library. I'm also installing Selenium Screenshot, which will be used to basically convert the HTML to image. The latest version of the Transformers library, PyTorch Lightning, which we are going to use for training. Then I'm using the ptesseract for the OCR that we are going to do on the images. And then I'm going to hack around PO requirements because Selenium Screenshot doesn't work with actually a newer version of PO. And then I'm using the Chromium. I'm installing the Chromium Chrome driver, which is the Selenium driver for Chrome. And then we are going to use the Tesseract OCR, basically the binary of the OCR engine. And then this is the PyTesseract are the Python bindings for it. So after all of this is done, I'm going to take the dataset, and it is currently stored on my Google Drive folder. So I'm going to basically download it from there. And yeah, this should download it. All right, and this should give us a zip file with all the HTML files that we have in this dataset. So once this is downloaded, I should be able to unzip it. And the file is called financial documents. Here it is. It's around 3 megabytes, so it's a very small file. And yeah, I'm going to get this and extract it. And if I check the contents of this, you can see that now we have this folder, and I'm going to rename this to simply documents. And if I do the listing of the files again, you can see that we have these documents. So now that we have pretty much everything installed, I'm going to restart the runtime just in case that some of the dependencies need to be restarted so the bindings work correctly. And after this is done, I'm going to again copy and paste some of the imports that I have, so we don't have to retype them. So here I'm importing most of the LayoutLM version 3 dependencies that we're going to use. We are going to use this feature extractor, the tokenizer, the processor, which are going to dive a bit deeper later. And then we have the model itself, which is LayoutLM version 3 for sequence classification. So this will basically classify our sequences into the 5 different classes that we have. Then I'm installing or importing the WebDriver from Selenium, then the screenshot library, and then some helper functions that we are going to use along the way, or dependencies. And then I'm basically inserting the Chrome driver binary into the system path. So the WebDriver is pretty much able to find where this Chrome driver is. So the next thing that I'm going to show you is the naming convention in the documents, or the folders at least. And if we check this, you can see that we have balance sheets, orders, etc. But I don't really like this naming convention, so I'm going to convert it into a snake case. And for each directory here, I'm going to rename it into the lowercase snake case version of it. All right. And then I'm going to pretty much do the same thing just to make sure that everything is renamed correctly. Okay, so we have the snake case for all of the classes right here. So this is great. Next, as I've already told you, we have like those documents are in HTML format. And if I download this and open it, you can see that we have some document right here. So if I would want to convert those into images, I would need an output directory for that. So I'm going to basically take all of the directories here and create an images directory for them. I'll show you in a second. So again, iterating over all directories and creating a directory for the images. So I'm going to create this directory name. So basically copy and paste exactly the same thing, but instead of documents, I'm going to rename this to images. And this should be able to create this. So I'm going to just double check and make sure that this is done. Yeah, so we have exactly the same structure as the documents. So this is great. Next, I will need the Chrome WebDriver for Selenium to initialize it and then start getting those HTML documents into images. So for that, I'm going to create a function called create Chrome driver. And I went into the habit of specifying at least the return type and the parameter types of most of my functions, or all of them. I think that's a good practice, and it helps when you want to use some helps from your IDE. So first I'm going to create these options. And I'm going to add an argument basically for the CLI that we want this to be headless because we are using Ubuntu server behind Google Co-op. Then I want to be not in a sandbox environment. And then I'm going to disable def shim usage. And this is pretty much because we need to load local files instead of remote URLs. So these hacks are, I believe, required in order for the local files to load. But if not, say that in the comments. And here I'm going to instantiate the Chrome driver with the options, which are actually the Chrome options. So let's have a look if we can actually create a driver with those. Yeah. And it says that it is returning web driver. So this is good. Let me just run through this. So we have a session and a web driver, which is all good. And then I'm going to build a function that is called convert HTML to image, which is going to get a driver, or this driver actually, then get a file path to the HTML file and a file path or directory for the images. And basically it's going to get the HTML, convert it, make a screenshot of it in the browser, and then convert that or save that into the images folder. So first I need to get the file, and I would need content slash and convert the file path to a string. So this is pretty much the protocol that you need to use to load a local file. So now that the driver has the file, I can initiate the screenshot. And then I'm going to take a shot, full screenshot, a very bad naming convention, I know, from this library. So I'm going to pass in the driver and the save path, which is going to be the images dir. And then the file path parent directory and the name of the directory. This will basically point to notes, balance sheets, etc. And this is the path, and the file name itself is going to be the file path, but we are going to replace the suffix with .png and then get the name of the file. And as a result, I'm going to return the image URL. Run this function. So next I'm going to take document paths of the first, let's say, 10 documents that we have, or the HTMLs. So let me check those. Okay, so we have some HTML files. And for each of those documents, I'm going to convert them to an image. And now that the process has started, you can basically see that it's not very fast to do so. It takes some time. So for around 2,500 documents, we can be pretty much sure that we have to wait, or we can use probably some sort of smart multi-threading if that's possible with Selenium. Okay, so now that some of the images or all of the images are now converted in about 30 seconds for 10 documents, I'm going to take the images have a look at those paths. Okay, so we have some PNGs here, And I'm going to basically use view image to open an image and convert it to an RGB format and basically show it. So yeah, here is some example from the image paths. Another example. So let's stick with this one, or maybe, yeah, this one is a bit better. So you can see that we have some sort of table with financial statement or something like this, lots of numbers, etc. So next, what I'm going to show you is how you can use this image and feed it into the preprocessor of LayoutLM version 3. So now we're ready to hop into LayoutLM version 3, and the Transformers library by HuggingFace has these pretty well documented examples of the original paper itself, which is again created or provided or researched by Microsoft and some very smart people there. And you can see that we have a feature extractor, tokenizer, processor, model, sequence classifier, token classifier, and question answering model. And these are pretty much different types of heads for the LayoutLM version 3 model. But in here, I'm going to start with having a look at the feature extractor, the tokenizer, and the processor. So as you can see, the only input that we have so far for this model is only this image. So to get to the point that we have like words, extracted words, we are going to use an OCR. And except for the words, we also need the bounding boxes of those words, which is again provided by the OCR. And then we have the image itself. So let's start by building or getting the feature extractor first. And the feature extractor is already imported. And I'm going to specify that we need to add the application of OCR. And I'm going to say that the language of the OCR is English. Why we need OCR? Basically because we have to have a way to understand the characters or the words and the bounding boxes for the model. And this will use the Tesseract OCR, which is frankly not a very not quite a performant OCR. But for those examples, we're going to have to use that. You can probably use Amazon or Google OCR, which are going to probably give you much better results. But again, for this couple of videos, we're going to do just fine with Tesseract. Then the tokenizer we're going to use here, which is LayoutLM version 3 tokenizer fast, which is implemented in Rust. And here I'm going to use the LayoutLM version 3 base model. So this will be the wide version of the model. And finally, I'm going to combine these into a LayoutLM version 3 processor, which expects a feature extractor and a tokenizer. So once this is run, this is going to go ahead and basically download the vocabulary for the tokenizer and the weights. So this is pretty much everything that you need thus far. And calling this processor, which does the heavy work for us, is very similar to a tokenizer. I'm going to pass in the image. I want the max length of the tokens to be 512. Then I'm going to set a padding to max length. Then I want truncation. And the returned tensors to be into PyTorch format. Let's have a look of what this encoding will be. So this will go ahead and use the extractor, which will apply the Tesseract engine, and a bit more stuff that I'm going to go into a bit more details later, and then the tokenizer on those words and bounding boxes. And as an output, we have the input IDs, the attention mask, bounding box, and pixel values. So this will be for the image embedding. This will be for the bounding box of the words. And those words are already tokenized using the tokenizer that we passed in. So if you're a bit interested into the shapes of those tensors, I've prepared this summary of it. So the input IDs are the maximum length that we've passed in. Then for the word boxes, we have exactly the same number of word boxes as there were for the input IDs. But for each bounding box, we have 4 values. And this will be the left of the bounding box, the top, the right, and the bottom. And interesting thing about this is that for the padding tokens, we also need to have padding word boxes. Then for the image data, we have like 3 channels for the colors and 224 by 224. So it's a square image that is converted from originally a non-square image, as you can see here. Okay, so how all of this works, I'm going to continue with the feature extractor. And if we just print it out, it should basically give you an overview or a summary of its configuration. So it does resizing, normalizations, and it applies OCR. And we have the image mean and image standard deviation that are used for the normalization. And then we have the size of the image. So how this works, I'm going to use the extractor on the image. And this will basically again run tesseract for us. And if we have a look at the features keys, you can see that we have the pixel value, the words, and the boxes here. And from this, you can get the images, the number of words, 186, so much less than 512, and the number of word boxes, which should always be the same as the number of words. So this is pretty good. And yeah, let's basically go ahead and look at a bounding box, just so you know what it looks like. So these are some of the bounding boxes that we can have. But let's continue with an image, actually. And the image data is going to be taken from the pixel values. And this has this shape, as you already saw from here. We have the 3 colors for RGB and then 224 by 224. So I'm going to basically swap the color channel and swap it at the back. Transpose this dimensions and put that at the back. All right, so now the channels are at the end. And yeah, I would have to, in order to show you what the final images is saw by the model, we can have a look at the image data and see that the actual numbers are actually floats. So we need numbers that are ranging from 0 to 25. And I'm going to need to convert those to integers. To do that, I'm going to use NumPy, convert them numbers to unsigned integers of 8-bit precision, and multiply the image data by 255. And now this should give us correct numbers right here. And the final thing is that I need to open the image from a NumPy array. In RGB mode. And this is pretty much the image that is fed into the model after the feature extractor has done its work. So this is pretty cool. This is the document, and this is the square of the image that is fed into our model embedding. Next, let's continue with the words and the bounding boxes. What is happening there? So we now saw what the images is. And for the words, let's take the words and the bounding boxes. Since we are not working with batch data, but only single examples, I need to get the first elements. And if I print the first, let's say 5 words and the first bounding boxes, first 5 bounding boxes from here. So you can see that we have these words, not the financial statements, which should be at the top left of the document. Here they are. And we have the corresponding bounding boxes. Again, the bounding boxes are left, top, right, bottom, and they should be normalized between 0 and 1000 in those ranges. And since we have the original image and since we have the bounding boxes with the words, I can pretty much draw the bounding boxes on the image. Let's start by opening the image itself again. Let's get this one. All right, and I need to rescale them because I told you that we need into 1000 range. And then I'm going to start to draw on the image. And for each word and bounding box, for each bounding box in bounding boxes, I'm going to draw a rectangle with a blue outline and a width of 2. And here I'm going to take the bounding boxes and convert the scale. All right, and finally I'm going to show you the image. So I'm going to draw basically each bounding box on this document. And as you can see, at least the bounding boxes are very well defined. So yeah, we have a basic understanding of how all of this works. So we're giving these bounding boxes, the words themselves, and the image to the model. All right, so how does the tokenizer works? So you can see that this has some parameters as well, and this is the vocabulary size. For the tokenizer, we are going to use text, which are the words that we have from the OCR engine or the feature extractor. Then the bounding boxes, and again I'm going to pass in the max length, then the padding, truncation, I want it, and the return tensors, I want those to be into PyTorch. And again, if I go to the encoding, I can see that we have pretty much the bounding box and the input IDs and the attention mask. So now what I need to do is to have a look at the different type of tokens that we have. And to do that, I'm going to use the Tokenizer and convert IDs to tokens. Then I'm going to take the encoding input IDs, and I want this to skip the special tokens. I want to have a look at the first 20 tokens. And as you can see, we have some weird characters in here. So let's fix this. To actually get a string and clean up this mess, I need to convert tokens to string. And when I pass in the first 20 tokens, you can see that now the text is finally cleared up. Notes the financial statement as at December 31st. So the last step in this video is to have a look at how we can use the model itself to pass in as example input. And to do that, I'm going to go and run the model or download it. And if you don't have this model, this should go ahead and download it, but I already did that. And this is pretty much normal because we haven't tried the model. And if we go through the config, you can see that we have a visual embedding right here. We have the version of the PyTorch library or Transformers library. And then we have the 2D embedding size, relative positions, etc. We have the attention heads. Some of the stuff are very similar to BERT or similar transformer models. And I'm going to use the processor to pass in an image. And then I'm going to pass in this encoding through the model and get the outputs or the classification of the model. Unfortunately, we have this deprecation warning, which is perfectly normal. This is something from the Transformers library. And then since we have only two classes for this model, which we're going to change in the future, these are the widgets that we get from the output of the model. Of course, this model has never seen our data. So in the next couple of videos, we are going to fine-tune the model using our data and devise a training pipeline using PyTorch Lightning. And yeah, in the next couple of videos, we are going to continue with that. So thanks for watching. Please like, share, and subscribe. Let me know if you have any questions in the comments down below. Once these series are done, I'm going to share the Google Co-op notebook on GitHub, and you can probably go through it yourself. Thanks for watching, guys. I'll see you in the next one. Bye bye.